new devices and how they can be used in multiple astrophysics experiments, particularly the ones that we are working in Delaware. Yeah, but first of all, just if people ask where Delaware is, it's basically a very small state between New York and Washington, D.C. And here's a short outline of my today's talk. So I'll start with the motivations and briefly mention why we're interested in the RFSoC technology, and then describe the technology itself, and talk a little bit about what we learned so far doing the work with those boards. And
excuse me, I think your mic is off.
Oh, sorry. Oh, is it better?
Yeah.
Oh, yes, yeah, sorry for that. Yeah, and basically then I will just show a couple of useful links that were extremely helpful, at least for me when I was working with this things, and then a short conclusion. All right, so I'm involved in multiple experiments, mostly for astroparticle physics, in particular IceCube, including Gen 2, and then POEO is a payload for ultra-high energy observation, so it's a balloon-borne experiment which flies around Antarctica, and RFSoC, it's a radio neutrino observatory in Greenland, and some others, and most of them use radio signals to detect, in particular, neutrinos or ultra-high energy cosmic rays. So essentially, the signals are coming from either Ascarian radiation or geomagnetic radiation, and a lot of those experiments sometimes share common requirements. In particular, so since we're talking about similar radio frequency signals in a similar bandwidth between like 100 megahertz to like 1.5 gigahertz to gigahertz, we can basically try to develop the same DAQ system using the same bandwidth, right? And some of the experiments require long and multiple buffers. So for instance, we had this idea of basically simultaneously reading IceCube surface array and the main IceCube optical system, and the buffers there has to be like seconds, so like 10 seconds, which is enormous. And sometimes, yeah, for POEO, you also want to have like multiple buffers to do like beamforming and all other things like that. In addition to that, a lot of projects involve an arbitrary signal generator being used as some sort of a transmitter for first seen as a calibration of the medium. So for instance, like an RFSoC or like other experiments using Ascarian radiation like Ariana or IceCube Gen 2. So what we do, we lower a transmitter inside ice and basically just like pulsing and recording the signals in using a receiver antenna somewhere, I don't know, like a couple of kilometers away or a few hundred meters away, because ice itself is actually not as simple as it looks like. So you really need to understand the properties of ice to better reconstruct your signals and basically to see how the signal propagates through this medium. And also, for instance, like for POEO, right now we're working on building some sort of a custom test bench for DAQ. So the idea here, you have multiple channel signal generator, and you insert the simulated signals, let's say, from neutrinos, noise, like anthropogenic noise, so like thermal noise, all this type of things, and you really want to like somehow synchronize them very well to set custom delays to basically test your DAQ very well, because it's very essential for this type of things. And also, a lot of those projects share one more requirement, which is beamforming. So the idea here is basically you create a phase array of multiple antennas. So essentially, like if you have few antennas, you just like you align the phases, and this multiple antennas essentially act as the one large antenna, which significantly increases your signal to noise ratio, which is very powerful, especially when you're looking for tiny signals coming, let's say, from ultra high energy neutrino interacting with ice and producing this Ascarian radio emission. And the new technology by Xilinx, basically a radio frequency system on chip, seems to be a good solution for both DAQ and transmitter parts for some of those experiments. And I think what is very important here is that it could be flexible. So for instance, we can use the same chip and use it as a transmitter, and then, I don't know, we build a DAQ based on the same chip, and we can share a lot of modules and like code or whatever. And yeah, in this, like I call it very general talk, I'll try to summarize what we've learned so far when we worked with those devices and corresponding tools and IPs. And yeah, I hope someone will find it useful as well. Oh, sorry. So basically, it's a general idea of RFSoC. It's very cool, actually. Essentially, you have a system of chip, plus you have, on the same chip, you have ADCs and DACs. So it's like MPSoC, essentially, with added ADCs and DACs. So you have a PL system, right, which is FPGA, essentially. Then you have PS. Basically, you have two processors, one for low-level real-time control, the second one is more powerful, where you basically run operating system like Beta Linux. And then what is very interesting for us specifically is that in the same chip you already have ADCs. So depending on the option of the chip, you have up to 16 of them, and they are either 12 or 14 bits. And yeah, the modern ones are now, most of them are 14 bits, and they can sample up to 5 gigasamples per second. And you have also up to 16 DACs, and they're also 14 bits, and they can basically operate with this sampling rate almost up to 10 gigasamples per second. Here it is basically a simple diagram. So here's your FPGA, and here you have this RF data converters, and you see they're organized in some sort of tiles. And here's your processing system, and here's this front-end error correction system. We don't really use it, but apparently it's super useful for the main application of those devices, like a communication, like 5G or like a future thing. So our experiments are obviously not the main goal of Xilinx, not the main target for these devices for Xilinx. Okay, here just like put a screenshot from Xilinx website showing what chips are currently available. So there's 3 generations so far, and to be honest, right now, like the price is almost identical for Gen 3 or Gen 2 or Gen 1. So there's just easier if you want to start working with them. Just much easier to go with Gen 3. You'll have all the advantages of the previous generations for the same price, essentially. And you see they come in different numbers of ADCs and DACs and different sampling rates, and different speeds, etc. So there are quite a few options which can be chosen. All right, and the main model, the main IP provided by Xilinx, at least like main IP for us working with those devices, is this RF data converter. So I call it a key component for those systems. Here, just like a diagram was covered here. So as I said, you have up to 16 transmitters and 16 receivers, and they all organized in tiles. So depending on the generation, so it could be either 4 tiles or for 4 ADC it will be 4 tiles, but the ADCs could be either 12 bits or 14 bits, and for DACs, for Gen 3 it's it could be either 1 or 2. I think I made a mistake here, so one of them should be DAC, but yeah, sorry, I'll correct the slides. But basically, the main idea is that all those ADCs and DACs are organized in tiles, and each tile is clocked independently, which is apparently great for, I don't know, like 5G technology when you need to transmit signals over, I don't know, maximum distance with less power. But for us, it's actually a problem, because when we want to do beamforming, we want everything to be synchronized very well, and having each block clocked independently is actually a little bit an obstacle for us. However, Xilinx has this feature called multi-tile synchronization, which again is super useful for beamforming, which is one of the most essential ideas for the experiments I just mentioned. So the idea here, again, you have multiple ADC or DAC. In this case, it doesn't really make a huge difference. And what you want to make sure is that all the data coming in or out are very well synchronized. So not only it starts at the same time, but also the delays and latency is the same for the tiles. And yeah, of course, you need a very stable reference clock for that. And RF data converter IP has this feature which works almost out of the box. I mean, it works perfectly with the standard examples that Xilinx provide. But if you want to change something, of course, it's not as simple. But nevertheless, it works great. And if anyone is interested, just like I put a link over here for MTS overlay from Xilinx, where they show how it works. And yeah, of course, we confirm it on multiple boards, and it's really, really impressive how we can synchronize these multiple types very, very well. All right, and for the software, so again, as I mentioned, we want to have the systems being as flexible as possible, and ideally, of course, we want multiple people working on those projects, in particular, I don't know, grad students or master students who just can come and start working right away. And yeah, it's probably not a secret that, I don't know, asking a grad student to write a firmware like in Vivado, it's from scratch. It can take some time. So for this purpose, yes, Xilinx and has very nice feature, ping. So basically, you have a Peta Linux running on one of the processors, and then you just literally talk to it using web browser and Jupyter Notebook. But of course, for firmware, you cannot avoid using Vivado. And of course, yeah, I know some of our colleagues using MATLAB and Simulink, but I personally never did it. So I myself, I use Vitis, so directly ping with Jupyter. And again, if you get RFSoC evaluation board, you can start working with it right away. So basically, just a quick example of spectrum analyzer, so which basically uses both DAC and ADC. So you inject a signal from DAC into your ADC, and you literally do a spectrum analysis from it. And you put some links on useful resources over here. All right, and there are a few evaluation boards for that, and most of them are going directly from Xilinx. So you see like Gen 2, Gen 3, and Gen 1 boards, but they're rather expensive. So each of them are more than $10,000, which is, I mean, the chip itself is not cheap as well. So it's like almost 10K. So it's quite pricey to start working with them right away. However, Xilinx has this academic version of RFSoC 4x2. So basically, you can get it essentially for free. For $2,000, you get it, but you need to get an approval from Xilinx. In my case, it was very fast because it was in the very, very beginning. But now I heard that people say that it takes a few weeks to get approval for them, and basically, you get this very nice board which can do a lot of things. So it has a Gen 3 chip, which has 8 ADCs and 8 DACs, but only 4 ADCs and 2 DACs are actually active. So they literally just physically connected to those SMA connectors. And they have a bunch of memory and interfaces, etc. And it already comes with a ping image. So you literally just like upload this image on a SD card and start working with it right away. And of course, for the projects like, I don't know, a balloon project or, I don't know, Ice Cube or, I don't know, Dream Greenland, so power consumption is always an issue because you're running autonomously, right, either using a solar panels or wind turbines or things like that. So power is a big problem. And those devices are not really low power, but yeah, the very first check with these boards that we did, just like we're running it at a maximum speed essentially, and we saw that it draws about 25 watts, which is still a lot, but yeah, it also does a lot. And we also started working with a new board, which is like an actual Xilinx evaluation board with a Gen 3 chip as well, which has all 8 ADCs and 8 DACs. So hopefully soon we will have some sort of a test DAQ system for Ice Cube surface array. So we want to see how the system can be applied for this project. All right. So here I just like put a list of the useful resources that I was using, because there are a lot of articles and I don't know, documents online, but unfortunately not all of them are good. And I just like put here the links on the information that I found very useful myself, which helped us a lot in this journey towards using the RFSoCs for multiple stuff. Okay, just a short conclusion. So as I said, those chips can be good candidates for multiple projects for both RX part and TX part. So of course, everything in one chip, so the hardware design is simple. And I think one of the biggest advantages here is also flexibility. So you can use the same chip, for instance, for transmitter and then for receiver, and you can reuse a lot of models. And you can also split tasks between people. So for instance, yeah, like what we do, so some grad students working on a PS side, so they work on Pink and then doing all the tests. For instance, you run a board as a network analyzer right away. So basically you just like create a bit stream, give it to someone, and they can just like use the devices, I don't know, check the performance of a filter or I don't know, amplifier, etc. So it's very simple. I mean, no, not simple, but saves a lot of time. And then this Pink environment, so it gives a unique opportunity to start working with the devices right away. So literally, you just like connect basically SSH to the board and run Jupyter notebook on it, and it's again very good entrance point for someone like who just joins the project and wants to understand how it's working. So no special knowledge really required here. However, there are still some disadvantages. Of course, they are pricey. As I said, the chip itself could be like around $10,000, and it's not very easy to get them. So I don't think you can get the chip itself. So you need to get it with some sort of a board from various companies. And power consumption may be too high. So for instance, yeah, as I said, like at South Pole or Greenland on a balloon, we're really limited in power. And for instance, for Gen 2 radio, I mean, I skip Gen 2 radio, the power seems to be a little bit too high. But yeah, we're looking into some ways how to reduce it. And since it's a new technology, still not a lot of resources, and still a lot of bugs, both in examples that I don't know, like companies, vendors provide, and also the documentation. Unfortunately, sometimes has bugs. So that's why, yeah, I put just those links. So if people are interested, they can check them out. Yeah, thank you.
Thank you very much. Very educative overview. Thank you. Do we have any questions? Maybe just a quick one.
Hello. That's a very nice presentation and also nice advertisement of this chip. But I got an impression that you have not really checked the prices of these components.
I mean, so basically you cannot get the chip itself, right? So you need to go through companies. So I've been in touch with 2 companies, and ironically, like not anyone from US actually was interested. So I was in touch with a company, one in Germany, one actually here in Switzerland. And you can get like a board with a chip with I don't know, memory and I don't know, like a fancy connectors, I don't know how they call it, like very like 100 pins or whatever, for roughly $10,000. So that's why I say a chip would cost around $10,000. But I mean, of course, the chip itself is cheaper. But yeah, they also like need to get I don't know, some benefit from.
I would say not really. You get this nice evaluation board for 2,000 something thousand euro. I have checked the price of the chip. 35,000 euro.
Just chip?
Yes, just a chip. I have checked it in DigiKey, and this was this is 4 channels of DAC and ADC.
Yeah,
I can imagine what is the price for the 16.
No, I mean just yesterday I got a reply. So it's for another balloon project. It's from this company called Knowledge Resources. So like the company in Germany called Trends, and Pueo, for instance, in Pueo we use the boards right from them. And of course, like they do not show the price on the website. We need to ask for a quote, and it was always around 10K. So I don't know, maybe a DG key just, I don't know, they don't have much, just like, but for instance, like this one, so yeah, this is, I mean, you cannot get a lot of them, right? So I think you're limited by one. But this one, I got it recently, just like a couple of months ago for around 15,000, also from, I think it was Mauser or DG key. So I don't know, maybe it's a bit different in Europe, but yeah, I don't know. But I mean, you can get it, but it's still sometimes tricky. So I mean, if you want to have like 1,000 of them, I think it's very tricky, but here we're not talking about thousands, right? So we need like 10 maximum maybe.
Okay, thank you very much, Sasha, again. We can move on with the next talk.